1.5, more on functions, page 119 in the college algebra book. First thing we're going to talk about in this section has to do with increasing and decreasing in constant functions. All right, we had mentioned yesterday the whole idea of intervals. And we had talked about different things that happen in intervals. For example, if I put an xy axis here, okay, and I give you a graph like that, and let's say that this point is -5, and this is 2, and this is 7. Okay, one of the things that you recognize here is there is some points in this graph that things are changing around. So for example, from -infinity up through this point here, we'll call that -2. So from -infinity up through -2, that is an interval. And what is happening during that interval is that my graph is increasing. Okay, this all seems really, really obvious and simplistic. I promise it won't stay that way, because I know you guys want to go into really rough stuff. Okay, so that means it's increasing. Between the intervals of -2 and, let's make this 4, our graph is decreasing. And between 4 and 7, it's increasing again. Okay? So, increasing, decreasing, and let's say that from here to here, let's say that this is staying horizontal. That means from 7 to positive infinity, it's staying constant. Your y value is constant. So what you're doing is you're looking at your x values, and from your x values, plugging them in the function machine and seeing what your y values are doing. So notice between -5 and -2, what do you know about the comparison between -5 and -2? Compare the two. What do you know about -5 and -2? Okay. You know that's true, correct? Okay. So if from left to right your x values are increased, or I'm sorry, just a sec.
Yeah.
So we're going to call our x values there, our -5 and -2, A and B, just so that we can be consistent across the board. So what we're saying is, if you're on page 120, there's an increasing, decreasing, and constant function bubble there. A function f is said to be increasing. When I say a function f, I'm meaning the y value. Okay, as we go from -5 to -2, it's said to be increasing on, and this is important, on an open interval, and I will go into that in a minute, for all A and B in that interval. A must be less than B, so the left-hand side must be a number smaller than the right-hand side. And not only that, but the function of A will be less than the function of B. So notice what happens here in yellow. What is my f of A at this point right there? What's my f of A? That's my A. What's my f of A? What is that? 0. What's my y value at that point? That's what I mean when I say f of A. When you plug A in, what does it spit out? And so f of A can be compared to the y value. What is my f of B at that point? A number bigger than 0, obviously. So, is this a true statement? Is my f of a less than f of b? Yes. Therefore, that I am increasing on that interval from -5 to -2. All right, if my a is less than b, what happens if my f of a is greater than my f of b? What is happening there? It's going down. Because let's look at the second interval here. Let me erase some of my yellow stuff here. Well, let's just erase all of this. All right, so let's say, for instance, this is my a, and this is my b. So a is still less than b, but my f of a up here is going to be something like, well, let's just say maybe 3. And my f of b down here is going to be like -3. It's going to be below my x-axis, so it's going to be negative. So in this case, my f of a is larger than my f of b. So therefore, I am decreasing. Okay, and the last one is if my f of a equals f of b, then I'm constant. It's a horizontal line. Okay? It just means my y value for a and my y value for b are the same thing. Okay. That pretty easy to follow so far? What's happening? Sure, why not? All right, so looking at that drawing there, what would you say the intervals are when this graph is decreasing? On what intervals is this graph decreasing?
Infinity to -1.
Okay, negative infinity to where?
-1.
-1. Okay, where is it increasing?
3 to 5.
3 to 5, okay. And you're only looking at x values, aren't you? The y values are telling you whether you're increasing or decreasing. The x values give you the interval where it's increasing or decreasing. So far, when Seth was giving me decrease, he was just giving me the x values, negative infinity to -1. Increasing, all he did was gave me the x values, 3 and 5. All right, where does it stay constant? -1 to 3. Okay, again, all you're looking at are the x values. All right, let's look at the y values here. What did I say about a and b? When I put them in the function, it's going to be the function of a is less than the function of b. Do you see, or is for decreasing, do you see where f of a is greater than f of b? If you look at this graph, what's happening? My f of a is greater than my f of b. So that's how I know it's decreasing. My f of a is greater than my f of b. Okay? So that means that I'm going downhill and downhill, and then I'm going uphill where my f of I'm going uphill where my f of a is less than my f of b. And I'm staying constant where they're equal. Because notice my y values are the same here. So therefore, they're constant. Does that make sense how that all works together? Am I asking you if that makes sense too often? Okay. Let's get rid of a bunch of that stuff. All right, one of the things I want you to look at is this right here. You're always going to use, that's called open interval. You're always going to use open intervals when you're writing these. What does that little rounded parenthesis mean? Yes, you're not including the point. Okay. One of the things that you'll understand someday if you ever take calculus is that if you were to square off that point, you're saying an awful lot of information besides that you're including that point -1 in your answer. So if I had negative infinity and -1, and I had this squared off and this rounded, that symbol does not only mean that you include -1. In calculus, it means quite a bit more stuff than that. Not going to go into the ins and outs, but on page 121, there is a paragraph where it says, in calculus, the slope of a line tangent to the graph of a function at a particular point is used to determine whether the function is increasing, decreasing, or whatever. So we're not going to talk about all that and why it works, but just remember, when you're doing intervals, you want it rounded, unless for some reason they're telling you that it's a closed interval and it's inclusive there. Okay, look at the graph on page 121. We have, come on, erase strokes. We have a graph that looks somewhat similar to that. We have what is called a relative max and a relative minimum. So we've got a relative max and a relative min. All right, when we use the word relative in math, we're saying that that isn't necessarily the highest point on the graph or the lowest point on the graph, max, min. We're saying in the interval, in the graph that we're looking at, relative to what we see, it's the highest and lowest point. It may go higher and lower somewhere out in the boonies somewhere, and then you would call it absolute max and absolute min, and you won't get to that until calculus. But right now, the relative max and relative min is just what you're seeing right now. Okay? So, what we're looking at here is, at what point are we maxing out on this graph, relatively? This point right there is as high as we go, because this here goes into infinity, and this here goes into infinity, and it's off the graph. So we don't know if maybe way up here it changes direction. We don't care. All we're concerned about is what is happening right here. That's my relative area. Okay, so my relative max is the high point, or points. If you're talking 1 point, it's a maximum. If it's multiple, if it's plural, it would be maxima. Okay, so have fun with the Greek there. So maxima just means that there's more than one. So here and here would be our relative minimas. Okay, that's pretty much all there is to that. A relative maximum and a relative minimum. So that should pretty much do it for that. One of the things you'll notice on 122 is they give you an equation. They give you f of x equals 0.1 x cubed minus 0.6 x squared minus 0.1 x plus 2. Okay, got a real important question to ask you here. Looking at the equation, how many answers are there going to be? Looking at the graph, how many equations are there going to be? Do you remember how to determine how many answers there's going to be? Yeah, the x-intercepts. Those are your answers. Those are the roots of the equation. That's what you're looking for. Where does it cross the x-axis? So, the exponent up here, 3, tells you how many answers, and if you look at the graph, it's going to cross 3 times. It kind of helps you check. When you graph this thing, does it cross 3 times? No, well, I probably did something wrong. Okay. So, crosses 3 places. It crosses once at negative 0.0. Where Where did it go? I mean, how does that happen? It just kind of disappears. And then I don't know where it went.
It doesn't let you.
So here is a piecewise function. G of x equals the quantity of all that stuff. Okay, so notice there's some conditions here. What we're doing is we're saying that if the number we're using for x is a number less than 3, we plug it in the top equation. If the number that we are using for x is equal to 3 or bigger than 3, we plug it in the second part of the equation. Okay, so it depends on which number we're looking at. So if I were to use, if I were to make a graph, or one of these XY graph thingies here, data collection things, and if I were to say x is 0, which expression would I use? Top one or bottom one? I'd use the top one because 0 is less than 3. So then I would plug that number in the top one and get a y value of 3. If my problem was, or if my x value was 3, I would use the bottom equation. What would be my y value that it would spit out? -3, right? Because it says whenever I plug a number in for x, my y value is going to be the opposite of my x value. So if I plug 4 in, it's going to kick out a -4. Okay? So what I'm going to get there for a graph is I'm going to get a graph that consists of 2 linear equations. When I graph the 1/3 x plus 3, I'm going to get a graph that looks like this. It's going to have an open circle there at 3. Because I can't plug 3 in. 3 is not one of the answers, but all the way up to 3. So that's why I have to draw an open circle. When I'm talking about the second one, I'm going to get an answer that is a closed dot, and it's going to go this way. Oops, let's put my dot back. And it's going to go that way. So, if I put in any positive number, will it always give me a negative?
Yes.
Only when that positive number is above 3 or 3. Notice the graph. It starts here at x equals 3 and goes down negative as my x value gets higher and higher. Okay? So that's what a piecewise problem looks like. Is you look and, I mean, it just says whatever you decide for x is fine. Pick any number you want. But if you pick a number less than 3, you have to use the top graph to find your y value and then graph it. If you pick a number equal to 3 or greater, you have to use the bottom equation. Okay? I don't know why they call it a piecewise function. Piecewise, I'm not clicking, but M for slope doesn't click either. So anyway, that's what it looks like. It's basically 2 different graphs. Sometimes those graphs intersect. Sometimes they don't. Sometimes they give you something like example 6 on page 125. They give you 3 different things. If you use the equation, or the f of x of 4, f of x of 4 minus x squared, and f of x of 2x minus 6. Okay? So, couple different options there for your piecewise. And you get a graph, like on the bottom of page 125, that is going to, in essence, give you 3 graphs. It's just 2 of them are morphed together because they have some commonality in there. So, does that seem simple enough, at least at this point, what a piecewise graph does and how to graph one? You just look at the number that you're going to use for x, and then you determine which equation you're going to use based on the rules. There's the rules that I circled there. Look and see what the rules are for that number, and if that number fits into one of those 2, use one of those 2 expressions in order to solve that. Okay, so that's 1.5. The only thing we didn't do in 1.5 is greatest integer function, and we'll get into more of that later.